may not have been an accident for him, but if I tried that, it would be an accident. So there are two problems with that. First of all, the one I just mentioned, the other was it was a Navy guy, but it was it was pretty good. So we are looking again at the fact that design points to God. Design points to a designer. Tonight we're going to look at a systems engineering approach, which is new within the last 3 or 4 years as far as a real focused effort by folks who are in this intelligent design movement trying to point to God. And my goal is to make it understandable. I promise you, you're going to be overwhelmed. That's part of the goal. So don't try to grasp everything. There are slides where I will go very quick through bullet points and and skip all the detail. It'll be if you want to download it later, you'll be able to download it later and do some more study if it interests you enough to go deep. But the idea is that this field is so rich and has so much to offer in terms of design that it completely blows away anybody who is objectively looking at whether or not there's a designer. And so my goal is to overwhelm you and have some fun, okay? So here's what we're going to do. We're going to have, we'll have 4 separate main topics. We'll do engineering, showing that it's from the Bible. It's God's idea. All this stuff. Scripture is rich with God's design involvement, direction. We'll look at a biological case study, which will be overwhelming. We'll look at a simpler case study that even I can understand. And so hopefully you guys, if you're smarter than me, so you'll be able to understand it as well. And then we'll look at what it is to build a system. What makes a system different from a simple object? And why is a system that has multiple things that it does, why is that a good case study for what we're trying to prove? So we'll start with part 1, engineering being God's design, God's idea. And we'll just run through some verses that kind of make that point. So in Genesis, God forms man from the dust of the ground, breathed into his nostrils the breath of life, and man became a living being. So he is the author of life. It highlights God's ability to design life. Genesis 1:1, he made the heavens and the earth. He's an architect. In Hebrews, every house is built by someone, but God is the builder of everything. So we have this idea that God is not just the designer, but he actually built it from scratch. He is an intentional designer. He made, at a specific point in time, he chose to do this. So there's intentionality. Then God said, let us make mankind in our image, in our likeness. And again, at a specific point, he created mankind in his own image, which makes us different from all the animals we studied 2 weeks ago in that respect. So he's the designer of humanity. He's deliberate and purposeful. He's efficient as well. He made everything for its purpose in Proverbs. In Isaiah, he's creative and innovative. Forget the former things. I do not dwell on the past. I am doing a new thing. Things that had never been done before. God is doing new things. He was creative. Now it springs forth. Do you not perceive it? I'm making a way in the wilderness and paths in the wasteland. So even during our progress here as humans on earth, God was changing things up at various points. This is an interesting one. I've thought about this one a long time, and I was glad to see this verse. The gold of that land is good. Aromatic resin and onyx are also there. God is the one who put the raw materials into the earth to be found by us. Have you ever thought about the fact that very early in Genesis, there are metal workers? God gave people skills. Now, have any of you been to like an iron ore or a copper mine? Who would think of getting rock out of the earth, grinding it, concentrating it, then melting it into a metal? Who would think of a rock turning? I think God taught people how to be metallurgists, and he gave them that skill set. He uses building analogies. So in 1 Corinthians, we see Paul talking about what it is to have an expert builder and a foundation, and he's using that for spiritual growth. So he uses that as an analogy because people understand what it is to build things as humans. So the scripture, again, is rich with ideas that God is the builder. He teaches engineering. Cain built a city. Noah built an ark. He was a shipbuilder. He builds for a specific purpose. Solomon built a temple, so sometimes we have people building things to glorify God. Other times, in the Tower of Babel, we have people building things for evil purposes, using that creative gift that God has given us for a purpose for which he did not intend, which is the very definition of sin. And then Tubal-Cain made things out of bronze and iron, so metallurgy again was God's idea. So that's, again, in Scripture, so we can see that God is a designer and a builder. So let's just move on to the fun, challenging part, the biology part. So we're going to do a case study looking at a few specific aspects that are related to biology, not my field. You have no reason whatsoever to listen to me about anything that comes next, because it's not my expertise. Is Angela here? We have a doctor who comes sometimes, but she's not here. Anyway, but you can trust the experts that I'm going to put in front of you. So one thing that a graduate degree teaches you to do is how to not get in front and put other people in front, because they know what they're talking about and you don't. So a lot of it is learning references. So we're going to put a couple of really important thinkers in front of you. So this first case study comes from a couple of arguments that will come next. They come from the field of medicine and the idea of engineering. How do you put these biological things into practice? And there's an engineering parallel. And so we'll look at both the medical, the engineering, and causation. How do you start something working that wasn't working before? So I'm going to introduce you to two acquaintances who have written an incredible book called Your Designed Body. And it marries these two fields together, the fields of medicine and engineering. And the two guys are Howard Glicksman on the right and Steve Laufmann on the left. Laufmann is the engineer. Glicksman is the medical doctor who will describe some of the challenges that we face as biological people, biological entities. So we'll start with Steve Laufmann, the engineer, kind of introducing the ideas in this book. And I'm relying heavily on this book. That's where the expertise comes in. So these guys are really good thinkers.
The message of our book is really simple. There are billions and billions of ways to be dead and a very, very few ways to be alive. And the very few ways to be alive require some special properties of the body. Without all those properties in place, you're not going to make it. Without your skin, you'd be dead. If your heart beats too fast or too slow, you're dead. If you can't get iron through your gastrointestinal tract to make hemoglobin so your blood can carry oxygen to all those trillions of cells, you're dead. You know, if your liver doesn't have all the right properties or can't make all the right chemicals, you're dead. So there's just so many ways that your body can fail, and there's so few ways that it can work. To identify how special that is. I love Howard Glicksman because he's an expert in how the body fails. That's his job. He works in hospice. He knows pretty much every way your body can fail, and he's pretty good at deflecting those things. So he's inspirational. He's brilliant. He's got great insight. I love the guy.
Our book details everything that's required for the body to survive. As a physician who spends his days trying to keep people alive, I can speak from experience that I know how all the different systems in the body work together to keep it going. There's no question in my mind that this all requires built-in engineering, which points towards intelligent design.
So the book, again, is Your Designed Body. It's very readable. Some of these books are overly technical, but they really do a good job of boiling it down and then giving you the implications. So we're used to seeing oversimplified drawings in kids' textbooks, in school textbooks, and so on. So we see these cartoon drawings of the big picture of the nucleus of the atom, for example, of the cell. And that's great because we need kids to understand the big picture, but there's a lot more to the picture, and sometimes we don't go far enough for adults to understand that. So drawings have gotten better over the years. This is a little more complex drawing, but even the better drawings, this is, when you look at the the cell membrane, the cell membrane has two layers. One attracts water, one repels water. There's all kinds of pumps in the cell membrane that do various things to keep you alive. Without all those things working, you're dead. You know, you get the theme here? You're dead. So again, a lot of complexity. And so as our drawings have improved and we see more detail, especially with electron microscopes and so on, But no matter how much detail we show, there's more that we're not showing. And so this slide is obviously not doing what it's supposed to do. So I'm just going to summarize it. There's a lot of things that life is supposed to do. And we're just going to go fast through this because it all got corrupted until we get down to this one, which you may be able to read a little bit. No, it's going bad too. I had apparently a slide fail. See, these things are complicated, but life has to do a lot of things. It has to be able to metabolize. It has to be able to reproduce. It has to be able to grow. It has to be able to error correct. All these skill sets. I'll fix it in the next version. But anyway, so you can read some of these now. So the order, high degree of organization, dynamic metabolism. It has to do metabolism while it's doing whatever that function of that cell is supposed to be, whether it's the stomach or the muscle cells or whatever. And so there's a lot of things that life has to do, not the least of which is making corrections as the cell is being reproduced. So as the cell and the genetics are being reproduced, it's doing error correction. And then if you get injured, it's building back to what you're supposed to do. That's boggling my mind. Think about that. You have a cut and the skin cells reproduce in a way that reconstructs what was there before. Sometimes with a scar, but usually most of the time functional. It's just amazing. Okay, so as we look at a medical case study, the real question is, what does it take to be alive, right? And we've all seen this. We all recognize what it is to be alive. Because when the Frankenstein guy is just laying there, it might have all the parts in place, but it's not alive. But when it all comes together at some point, it's alive! It comes to life, right? So Glicksman and Laufmann would tell us between a living cell and the most highly ordered non-biological system, there is a chasm as vast and absolute as it is possible to conceive. Life is the greatest discontinuity in the universe. That difference between material that looks like it should function but it's dead, and a living cell and a living tissue, it's vast. And we don't really know what that life embodiment is. Another quote from their book, life never exists as a formless blob, but instead always exists in an architecturally complex form. Nor, of course, does life exist in the often fertile imaginations of materialist scientists. Life is found in the real world, and reality has a way of humbling theories that are not grounded in the nitty-gritty details of what life requires. There's a book by Greg Kokel that I like. It's on relativism, and his subtitle is something about when life bumps into reality. Because relativism doesn't work in the real world. A different topic. We won't go into that any further. Laufmann is going to say there are two hard problems. I think there are three. And so he'll say two on the second one, but it's actually three. So we'll go to the first one is becoming alive. Getting something dead alive. And God is the only one we know that can do that. So the origin of life and its necessary systems is really, really a hard problem. So the second one is staying alive once you are alive. So you got a baby, that's an incredible miracle, and then keeping that baby alive is a full-time job. Keeping ourselves alive takes a fair amount of effort. We wear seatbelts, we eat healthy some of the time. So staying alive in spite of challenges, sickness and illness. And then reproducing before you're dead. You've only got so long. Remember the monarch butterflies? They had to do that before their life cycle was over. And so these are the three big problems that they're going to outline. So real quick, the origin of life and necessary systems.
Okay, so there are two really hard problems in life. One is being alive. So, right, you have all these natural problems with physics, problems with fluid dynamics, problems with electrical currents that your body has to solve, problems turning photons into electrical signals and then having a brain that turns them into a visual system. These are the things you need to be alive, and they're very hard to do. So that's the first problem with being alive.
Life is a hard problem because first at the cellular level, the cell is surrounded by a cell membrane, and everything inside the cell has to stay there. The volume and the chemical concentration has to be kept under control, besides everything else that it makes and does. So it is exposed to the natural forces such as diffusion and osmosis, which if not controlled, the cell will die. And so for that, it has something called a sodium-potassium pump in the cell membrane, which spends 1/4 of your energy at rest getting rid of sodium and bringing potassium back into the cell to keep the cell stable. And then expanding from there, we have to go into a multicellular organism where all the cells in the body need a lot of chemicals such as oxygen and sugar, proteins, etc. But they can't get it from their environment, so we need to have multi-organ systems to provide that for them. So this is multiple problems that have to be solved.
So this guy is going to put it in language that we understand better, okay?
I've got some good news and some bad news. Bad news is
Everything is trying to kill you.
those french fries you just ate, probably clogging your arteries right now. Dead. Spiders, they want you dead. The sun wants you dead too. Legos on the floor. Instant death. The good news is, most things are actually sort of bad at killing you. Sun? Bam! Sunscreen. French fries? Bam! Eat some leaves. Legos? Bam! Shoes. Spooters? Also shoes. But, no matter how many shoes you have and leaves you eat, eventually, you will die. We all know that when a living thing dies, nature takes its course. An irreversible one-way path of decay begins. The bits that the thing was made of, its complex molecules, they start to degrade and become disorganized and smelly. This natural process is unavoidable, and we have all observed it. Surprisingly, some really smart people from Charles Darwin to scientists today believe that the opposite process has occurred. They say, a long time ago, purely natural processes somehow created and arranged molecules required for the first ever living organism from a primordial soup, and that led to life as we know it today. Maybe you've seen this contraption before. It's like in every biology textbook. Decades ago, these two scientists, Stanley Miller and Harold Urey, made this experiment to try and test if life can come from non-life, abiogenesis, sometimes called chemical evolution. Textbooks count the Miller-Urey experiment and others like it as evidence of this. The pictures painted that, with a few tweaks and enough time, they're just a hop, jump, and a skip away from creating life. They contend that under the right conditions, getting the building blocks of life is easy enough. And from there, life would flow naturally. But is this really the case? Let's take a look more closely. Simpler chemicals have indeed been transformed into some of the building blocks of life in the lab. That much is true. But how impressive is it? Well, about as impressive as water turning into ice. When the situation is right, water freezes. Pretty cool. Likewise, these building blocks form spontaneously as well when the situation is right. The important questions are, how do these lab experiments compare to reality, and how close do these building blocks get us to life? In other words, if we had the building blocks, will life flow naturally as the biology textbooks seem to indicate? One dirty little secret of these origin of life experiments is that they don't actually start with plausible natural conditions. These experimenters, I don't want to say cheated, let's say they cheated. They sort of just cheated. These scientists begin with pure industrial strength ingredients. These are never found in nature like that in such extreme concentrations and purity, certainly not all in the same location. billions of dollars worth of precise machinery created and operated by thousands of very intelligent people in labs all around the world over the course of many decades is what gets us to the point where these experiments can even begin. Another dirty little secret of these origin of life experiments lies in the presentation of their results. Even cheating like they did, what exactly do they end up with? The vast majority of what they make is actually toxic garbage. For example, in this paper, over 99% of what they make is not only unwanted, but effectively destroys the building block's ability to form more complex molecules. The very process that makes these building blocks also, critically, stops them dead in their tracks. A little detail your biology textbook may have left out. The third cheat is something called relay synthesis. They buy industrial strength ingredients to start with, make mostly garbage out of it, but may produce trace amounts of something they wanted. Like in this experiment, they yielded 0.011% of the nucleobase adenine. Then they declare success. These chemicals can technically be turned into adenine, even though it is unavailable to actually do anything because it's surrounded by garbage or consumed by side reactions and would quickly degrade, but whatever, details. For the next experiment, rather than starting with what the previous experiment actually produced, this mixture of garbage, instead they now feel justified in purchasing pure adenine from a laboratory supply shop to further cheat at the next step toward life. And this sort of thing happens over and over again, completely detached from reality.
But you admit they are using natural ingredients though, so what's the big deal?
Just to be clear, the experiments are trying to show that these building blocks can form in natural environmental conditions. So yes, these conditions are natural, only in the same sense that your cell phone is also made in natural conditions with natural ingredients. The metal in your cell phone is basically just some melted down rocks. The battery's more simple elements, lithium and cobalt. The glass screen, computer chips, and circuitry, just fancy melted sand. The apps and pictures on your phone, simply arrangements of electrons, another completely natural phenomenon. Every element of your smartphone can be broken down into naturally occurring components, just in concentrations and purities and arrangements never found in nature, very similar to these lab experiments. But you know, I've never seen a cell phone happen in nature, not even one of those old crummy ones you can only play Snake on. How natural things are arranged and their concentrations is key. If I made a cell phone in a lab using ingredients created in factories, am I really simulating a natural process? Or am I using intelligence to direct and create? Now, scientists do acknowledge that starting with these industrial strength chemicals is problematic, but they often express this in coded terms laden with jargon to make it sound less awful. Take this recent paper talking about their use of unnaturally high concentrations of ammonia. They say, this may limit the geographical areas where such chemistries may occur, an aspect that needs further investigation. Translation, nowhere on Earth could they ever expect to find the circumstances they contrived to reach the conclusions they wanted.
Yeah, but given enough time or enough planets in the universe, surely anything could happen. What if we had billions of years?
Some problems are not solvable by time. When people assume that lots of time is abiogenesis's best friend, it seems reasonable. But it's exactly wrong. They're not BFFs. At best, they're frenemies. Yes, time gives more opportunities for things to happen, but what's overlooked is that it also gives more opportunities for time to decay and destroy the trace amounts of biotic material that may have been created. Some of these molecules are very fragile. Their half-lives can span from merely decades, not millennia, all the way down to just days or even minutes. The origin of life is not like a very long journey by foot, where if you could just make a little bit of progress, just one single step, given enough time you could make it any distance. This is a problem of a different category. It's more akin to attempting to walk to the moon. Time won't help that sort of problem. Why not? Well, to give you a rough idea of how large the chasm is, these experiments have produced small molecules like this. And this is just some of what they need for even a very simple, single-celled organism. Thousands of chemical ingredients must be present in the same place at the same time, the correct concentrations, chirality, with no ability to tolerate anywhere near the level of impurity found in undirected chemical processes or in the lab. Living organisms handle this by making most of the chemicals they need for themselves, on-site and on demand. But of course that wouldn't be possible before they existed. The chasm between the starting point and the simplest possible life form is so large that abiogenesis is hopelessly and forever off limits to the mechanisms in question. It's not that there isn't enough time, it's nonsensical, like asking how heavy is blue. It's simply the wrong question, and it betrays an ignorance of the scope of the problems involved. In spite of the observable data and our own experience showing us that, left to its own devices, life only goes one way, toward decay and degradation, some still have faith that it could have gone the other way in the distant past with the origin of life. So, when you see statements like,
Life arose via chemical evolution,
that sounds scientific. But that claim is more akin to alchemy or a horoscope than to science. Lots of narrative and hope, but little actual evidence. And so they rely on imagination and people's scientific ignorance to be persuasive.
So don't be one of those people that's easily persuaded. So let's move right along to the next topic, which is reproducing before you're dead.
The second problem is reproducing life. So I got to make another body. That's an extraordinarily hard problem. And most people, because it happens all the time, just think that must be easy. It's just natural. But it is nothing of the kind. It's extraordinarily complicated. And if pretty much anything goes wrong, there's no next generation.
So reproducing, as we all know, is really complicated. Anybody who is a parent or anybody who's been a baby once should know that. So we'll just keep moving along. So physicians work in a set of parameters that are different than engineers, but there's a lot of overlap. So physicians know some certain things, like the body has to follow certain rules or you're dead, right? The body has to have some control. They talk in here about equilibrium, balance chemicals, not just balancing this way. But you have to keep the right concentration of chemicals inside the cell, and when they get out of whack, there's got to be a mechanism that corrects that, makes the right counterbalance, and balances the chemical problem. You have to be able to get the right stuff out from the products of metabolism and the right stuff in if you need an energy source. Those all require gatekeepers and controls. The body has to possess exactly the right functional capacities in all kinds of ways. The body has to be finely tuned. So lots of different ways that medicine addresses the biological needs. Engineers have a set of parameters that they think about as well. So systems require many parts. Systems have to be coherent. They have to be worked together. They have to be the right size, the right shape, the right interaction, the right touch points. You think about it like you have all these wires that have to be connected in exactly the right way, or we don't get a picture on the screen. All those things have to be sized properly. When we go to international places, the plugs don't work. Simple things like that. So it has to be coherent. Systems of systems usually exhibit complex interdependency, so they rely on each other. Without all the systems in place, none of them work independently. So for example, that when he was talking about you need iron to carry oxygen in the blood, but if you have too much iron, you die. You know, it's just this same problem keeps coming up. So anybody have any questions about biology? Because I don't have all the answers, but I know it's really complicated. Okay? Well, let's move to the next idea, and that's a simpler case study, one that even I can understand. So hopefully I'll be able to explain it to you in a way that's a little more comprehensible. So my background is aviation, so let's talk about airplanes. Okay, that's something I can communicate about a little easier. Every airplane is a set of compromises. Okay, so in this example, we have safety and cost. We have to balance those two. We got to be safe, but we got to be under budget. So let's take an even simpler airplane diagram. Okay, set of compromises. All right. So here's an airplane. If I move the wings backward on the fuselage, the airplane becomes more responsive because there's less distance between these 2 points. And so I have more responsiveness but less stability. I will probably go out of control while I'm trying to be more responsive. Not a great trade-off. If I move the wings too far forward, the center of gravity is such that this little tail surface can't lift the back of the airplane. So it's got to be in just the right spot, near the center of gravity. If I make the wings smaller, I have less drag, but I have to go a lot faster on takeoff and landing, which can put stress on landing gear, tires, all kinds of things can fail if I have to land at too high a speed. If I make the wings really big, I have a different problem. The airplane will glide better. It will probably glide more farther if my engines quit, but there's more drag, and so I can't go as far as I would be able to with the right sized wing. I'd like to have lots of power. Airplane drivers like power, okay? But if I make the engines too big, then they're going to use too much fuel, and again, I won't be able to go very far. Plus, with really big wings, that's what keeps the 737 limited. They can't put big enough gear on it. There's not enough room for the little tiny space between the engines for the gear to go down and lift the airplane up, have bigger engines under the wings. So you have, again, this set of compromises. So you end up with the right kind of airplane for the job you want to do. In this case, we want to carry people from point A to point B. Here's a different case study. This is in May of 1927. This is Charles Lindbergh. And in May of 1927, he first, from the 10th to the 12th of May, he flew from Los Angeles by way of St. Louis to what was then Roosevelt Field, now called LaGuardia Airport. And this is where my dad comes into the story, because we've got to bring him into the story at some point, right? So you remember this scenario. So on May 12th, he landed at Roosevelt Field. Now my dad gets in trouble again. He was born in 1917, so he's 10 years old. He's probably in 3rd or 4th grade, and maybe 4th grade, I'm not sure. But he looked out the window, and their school was close enough that he could see this airplane, and he looked out the window, saw Lindbergh's plane, knew exactly what it was. He said, "There's Lindy!" The whole class scrambles to the windows, destroying whatever was happening in the classroom. He gets in trouble one more time. But let's look at Lindbergh's airplane, okay? So Lindbergh's airplane is a unique design. It needs a lot of fuel, but it doesn't need a lot of visibility out the front. So this is an interior look at the cockpit from a Microsoft Flight Simulator. And you'll notice that you don't see forward very well, because what you have instead, this is a periscope. And this is the mirror over here that reflects into this mirror. And so if you're sitting in just the right spot, you can get a little reflection looking forward, and then in flight, this knob would move this over, pretty ingenious design, and it would close it up so there's less drag. Okay, so when you're taking off, you're not going to see very much. So you got some side view out the windows, but as you're going down the runway, you're kind of using your peripheral vision to keep yourself on the runway, but you're looking out the mirror to kind of keep yourself toward the center line. And this airplane is extremely heavy. It's got the maximum amount of fuel you could have so that it would still take off in the available runway space. And so as it gets airborne, if I was to play this clip longer, you would see it climbs very, very slowly. And so, but it's designed for a purpose. It's designed to go a long way. He's not on a sightseeing trip. He needs to be able to get a long distance, carry as much fuel as possible. And so it's a set of compromises. And so this design took those things into account. It had very big, for the size of the airplane, fuel tanks. And again, limited visibility. And so the fuel tanks, as the fuel burned off, the center of lift is right there, so that as the fuel burned off, the center of lift stayed pretty well where it started. So great design for the purpose he was trying to accomplish. And again, just a very unusual airplane in that we don't have a front windshield, which pilots like to look out. Well, here's an example of something that I built. This is a wall unit in our guest room, and it's built to be sort of camouflaged. And so on the front of this, there is a drop front desk that you wouldn't have expected, right? And we've never actually used it, but it's kind of cool. There was a spider over there. Stuff happens. And then it's not really doors, it's a Murphy bed. And every detail of this had to be measured, carefully cut, engineered. And so it's kind of a fun thing, and then you can fold it up and you can have your guests come over. But when I say I built it, I bought a kit. Okay? So I did all the wood parts, but the metal parts came in a kit. And the kit even had diagrams. Now it didn't have the side diagrams. I did this much. They've added this later, but I did that part. When you're building something for a purpose, you have to think through all those things. There are parts that would have hit each other if I'd built them too big or too small. So we design these things for a specific purpose. Let's go even simpler. This is an owl box. This year it's a squirrel box because the owls didn't come. But this is a couple years ago, and we had owls come up to this box, and they were there, and we had baby owls, and it was really kind of fun. And so this year, this was our visit in January of 2025, and we put it up. I think the next day we had an owl show up, and he kind of looked around, checked it out, and then they flew away, and they never came back. So it's a squirrel box this year. It's going to get taken down pretty quick. But even again, I built it, but there's more to the story, because I found some plans, and I built it according to the plans. And it showed the size, the ways you should cut the pieces out, and I made some modifications, but it shows even how to cut the pieces out of the wood. So there's a plan to this. But even then, there's more to the story, because there's a wood shop in my garage that I built both the Murphy bed and the owl box. But in the wood shop, you know, I've got some tools, and so I've got a workbench, and I've got a table saw, and I've got a chop saw, and a pneumatic nailer. I think I used the nailer, and the drill press. So you got all these tools. So, you know, it's really a cool thing to have thousands of dollars worth of woodworking equipment to build a $30 box, right? But the point is, I can build lots of things with wood. But even that's not the whole story, because I need infrastructure. I have this system of interacting systems that all have to work at the same time. And some of this is pretty sophisticated stuff, okay? So we have this infrastructure nested together, interacting in a way that allows us to do some relatively complex things, nothing like origin of life, okay? All right, so that's how one way to think about that aspect. So let's look at what a system of systems looks like, okay? In the human body, Laufmann and Glicksman, they kind of identify 11 different major systems that they write about. And they talk about the complexities of how these systems work. And this is where if you're, I found it fascinating, but I did skip through some of the stuff that were a little deep for me because I'm not a biologist, okay? But if these 11 systems don't work properly and don't interact together, any one of these systems not working, guess what? You are dead. You're getting it. Yeah. So then the question is, what is a system? How do we define what a system is? And so Laufmann, that's where Laufmann really comes in, and he's very, very good on explaining this stuff. So the first thing you need is a sensor to sense what is needed. Okay? So that's the first step. Then you need an integrator, and you can think of this as a robot, something on an assembly line, or something in the body. They all have the same functions. So an integrator analyzes the sensory information, makes decisions about required action, sends instructions for what's needed. And then you need what they describe as an effector that receives signals from the integrator, takes required action. So, case closed, right? Not so fast. Because then you have to go back to the start, to the sensor, and say, okay, we took these actions, were they effective? Do we need to go faster, slower? Am I producing too much and I'll kill whatever it is I'm trying to solve? So the sensor loop, feedback loop is continually integrating information to the effector so that the outcome is what we desire. Do we want to lower the salinity, or do we want to remove some other chemical? That's what this system has to do. Putting it into terms that I can understand better, so the sensor has to figure out what's wrong in something the system can fix. So if the system is designed to remove excess fluid, but it's not designed to balance the salinity, you're dead, right? So it has to be something that system can actually fix. The integrator determines what action can be taken and how that's to be put into place, and the effector receives signals from the integrator, takes the required action, and again you have this same loop. Putting it in a little bit more simple English for me. Okay, so what do systems have to do? Well, they have some roles that they have to play. They have to fix a problem. Okay, they have to sense what the problem is and fix it. They have to interact with other systems so that while other systems are fixing various problems, there's coordination that happens so they don't get in each other's way. And then there's, when you look at a schematic of what this system of sensors and integrators and effective things look like. So let's look at these things in a schematic to solve a specific problem, okay? So we're going to look at it this way. So the first problem, we'll only look at this one problem, but the problem, every cell in the body requires oxygen for respiration. Fairly simple thing, right? We need oxygen. Let's look at what that gets into. So that results in another problem. Most cells in the body are on the interior and they don't have access to oxygen. So how do we solve that? Well, that results in two more problems. We have to deliver oxygen to every cell in the body, but we have to get the oxygen from the environment. So how do we get the oxygen out of the air we're breathing and into every cell in your body? And then there's another problem. How many red blood cells do we make? If we make too many, that's too much iron. If we don't make enough, you suffocate and die. And then there's another problem. Where do we stage air for the oxygen so that it can be transferred to the cells? And so we now have our first solution. We have an enzyme that I can't pronounce that solves one of the red blood cell problems and how many red blood cells are produced. And it's a little bit fuzzy. But then we have two more problems, but we start having more solutions. So where do we stage the air? In the lungs. Cool. And how do we get the oxygen to the blood? Alveoli. Okay, so we're starting to get some solutions, but we're not done yet. We have two more problems, and we have a couple solutions now coming into play, and you can see what's happening. This cascading of problems that have to be solved gets more and more. And that's when you're building something, not so much with the birdhouse, okay, but with the Murphy bed. There were times when, oh, I thought I could do it this way, but it didn't work, and I had to rebuild a part. The drop-down desk was not part of the plans. That was something I brilliantly decided to add. It was far more energy than I needed to put into that. It was fun, but we never used it. So, did I mention we've never used that? So, anyway, but when you're trying to engineer these things, there are always roadblocks, and there are square corners you have to figure out how to get around. So, again, problems. Well, it turns out that in the body, there are things that we've talked about DNA, and we've alluded to the fact that DNA only does part of the work. So here's a really important article. It came out just last month, and I'll read the title to you. Heritable non-genetic information that is independent of DNA and that governs organismal development, tissue regeneration, and tumor architecture. Let's translate that, okay? What they're really saying is this: body characteristics inherited from parent organisms are not passed on only through the genetic code. The genetic code of DNA only does certain things. It solves for building proteins and some of the enzymes and that sort of thing, but it doesn't build everything. It helps, the DNA is really important in cellular functions. It doesn't have a body plan. So you get this muscle cell that reproduces, like in our first video. How does it know where to attach so that you form that muscle into a bicep or a thigh muscle? That information, the morphology, the body plan, the body shape, is not in the DNA. It's someplace else. Part of that information, we think, is in the gene regulatory network that is what we used to call junk DNA. Scientists aren't calling it that anymore. They're calling it the non-coding region. But in terms of what it does, it's actually the operating system for the cell. And a lot of the gene regulatory network. Remember when we talked about those 6 different layers that you can have of information a couple weeks ago when we were talking about genetics? That's all controlled, we think, in the non-coding regions. And now over 85% of the non-coding DNA in some organisms has been mapped. Still not enough for body plans and morphology. Okay, so let's look at the abstract, which is just as abstract as the title was. But if we highlight a few key words and then we extract those and put them into English, let me tell you what this actually says. So it says, numerous studies suggest the existence of a code that controls tissue structure has to exist apart from DNA. So we've got some code someplace, we're just not sure where. A term is needed to capture the 3D special codes in biology. Information is passed on to offspring, otherwise it would have disappeared during, they said evolution, I'm going to say during reproduction. Information observed in tissues is not reducible to the laws of physics because structures do not spontaneously form in liquid. You don't get accidental structures out of random chemicals in liquid. Physiological information, therefore, is necessary to build an organism. Instructional information that affects function without DNA program must be inherited in some other way. In other words, it's outside just the DNA that we thought was going to be the way to, the Rubik's Cube, the Rosetta Stone. We thought it was going to unlock all of the mysteries. Not quite. Okay. So that's a really important paper, but they're doing research on this stuff all the time and realizing how big the problem is. And it's like anything else in science or even in my field of history, the deeper you look, the more there is that you don't know. And you generate more questions than answers a lot of times when you're doing that kind of research. So let's look at the cell's electrical system. Did you know you have an electrical system in every cell? I thought this was brand new information, but this paper is from 2019 that we're going to look at. So there's actually signal processing in cells, and here's what it does. Cells process electrical signals using changes in membrane potential, primarily through the movement of ions across the cell membrane, which can lead to action potentials and are crucial for functions like nerve conduction, muscle contraction, and communication between cells. And there's research, again, from 2019, mechanism of electrical signaling in cells is revealed. And then this paragraph is really helpful. Researchers have now obtained the long sought after resting state structure of a voltage-gated sodium channel. Did you know you had a voltage-gated sodium channel in all of your cells? Somehow that was left out of my textbook. These types of channels in living cells form a voltage-regulated pore that allows rapid passage of positively charged sodium atoms across the cell membrane. This generates a tiny electrical signal. Electrical signals in nerve and muscle are crucial for learning, memory, movement, and many other physiological processes. Somehow that escaped my attention. But there's now we've got signal processing on the electrical level and non-genetic information residing someplace that we haven't discovered yet. So let's let Steve tell us a little bit more about that.
So when you talk about theories of origins, you need a theory that can overcome the causal hurdles, right? So that's what causal hurdles are. They require causal solutions. So when you look at neo-Darwinian theory and any of its incarnations, it really doesn't have much of any way to make anything new. And all the causal hurdles we've talked about require a lot of stuff in place, organized just right, connected just right, and orchestrated just right, or they don't work. So that's a huge causal hurdle. What in Darwinism can overcome that? And the answer is nothing. There's no theory of the generative. And you can read the third way neo-Darwinists, and they'll admit that Darwinism has no way to overcome these causal hurdles. That's why they're looking for something new, a new third way. The theory of biological design, like Darwinism, has specific mechanisms that each have capabilities and limitations. And when you look at the theory of biological design, which is, in some sense, it's sort of nascent, it's still early times. But when you look at the causal forces there are things like, I need an intentional actor. I need somebody that can overcome these causal hurdles. And that requires intention, and it requires the ability to act. Right? So when you compare these two theories side by side, you see that the neo-Darwinism is really, the way I like to say it is it's proven everything it will ever prove, which isn't actually very much, and it's exhausted. It has nothing else to offer. When you look at the theory of biological design, that means that there was a designer who intended these outcomes. Maybe not exactly the way we see them, but that intended to build in the rules, the capabilities to adapt to situations. And so in the new theory, organisms have the ability to adapt to changes in their environment. The environment isn't changing the organism. The environment only constrains the organism. So the organism itself either has to be able to adapt to the environment, to a change in the environment, or it will die. It's a pretty simple equation. The only way it can adapt is if it has built-in mechanisms for handling that change. So every organism then has a range of pre-designed environments that it can dwell in.
So again, I'm going to encourage you to take a look at this book, Your Designed Body. I think you'll find it's fascinating. And he goes into a lot more detail than we'll have time for. Obviously, any book would do that. But one of his strengths is thinking through implications. And so he has a number of corollaries that I chose not to put in today just because of not trying to overwhelm myself any more than I already did. But one of the corollaries is the more complex a system is, the more difficult it is to build, the more iterations of trial and error we would have to use to get it functional. And so the more complex it is, the harder it is to build. And so we have these incredibly complex biological pathways and chemical balancing mechanisms in the cells and in the body and just in metabolism that require multiple systems interacting. You know, it's great to be able to break down nutrients in our stomach, but if we don't have a blood system to circulate it to all the cells that need energy, it's not going to be effective in keeping so everything has to be working together. And so again, I'll leave that at that point and encourage you to do more research on this if you're interested. So the theory of biological design, we've alluded to this before, and I had an email conversation with Steve on this today. Just realizing that what we've described a lot of things about the theory of biological design, but we haven't really defined it very well. So it's a fairly new idea in the last couple of years. We really need to characterize it in a way that's as gripping as Origin of Species was for that generation. We need a new Origin of Species concept that is catchy, engaging, captures the idea. So, for example, Randy Galuzzi uses the term continuous environmental tracking to talk about this aspect of biology where the environment constrains an organism, and within those constraints, organisms can adapt to a certain extent. We talked about the blind cave fish. An animal can have a certain temperature range that can adapt. If it's a colder environment, the animals will develop more fur. If it's a warmer environment, they'll adapt to the temperature changes that they need to adjust to. But they can't ever change from a horse to a fish, or even from a horse to a mule. So the animals have limited amount of adaptability, but there is some pre-programmed adaptability, and so that's why I call it limited pre-programmed adaptability. They haven't bought that term yet, but there's all kinds of ways to characterize it. We just haven't found, I think, a great way to capture it that will move us forward. So we're working on that. But the theory of biological design has a number of attributes that are worth just outlining briefly. First of all, it has to cover the idea that there are intentional acts. It incorporates attributes from the outside the organism. So the organism senses its environment and has a certain amount of change that it can accomplish. But there's clear evidence of intervention in designing a system that would have that amount of adaptability. So your car can operate in very fast environments and very slow environments. It can operate in different temperature ranges. That's pre-programmed that it can do that. Now it can't change to adapt to different environments beyond what it's designed to do. But that's an example of there's a certain range in which, you know, every time you buy something, it'll tell you the voltage, 110, 220. You know, so it can go, if you go to Europe or Japan, you can plug it in, it can handle it. But if you go to a 440 world, you're going to burn it up, right? So it's got a limited amount of adaptability that's built into it. It has internal capabilities that are that show that there's some foresight. The designer knew that this thing was going to be used in a different environment. The designer knew that bears were going to be able to swim and catch fish, and also be on land and get berries and small animals. And so the designer knew what capabilities different animals would need, and he had the foresight to do that. But also the foresight to do things like, yes, you have a blood system that's capable of carrying oxygen around, but it also gets involved in clotting of the blood when you have an injury. So there's foresight. The designer knew that biology was going to be running into trees and needed to fix the scrape on its knee or its whatever, okay? Architecture. Again, we see properties that engineers would use in biology. So for example, we see design properties like modularity. We see the similar type of module, a stomach, in many, many different animals. That's evidence of common designer, not common ancestor. Okay, so there's no evidence, but then there's design, that's properties, design patterns, evidence of a common designer rather than common ancestor. Okay, so we've got patterns as well as properties. And then there's errors and degradation. Degradation will occur, the designer knew that, and so he built error correction in as the DNA is being transcribed in messenger DNA and transfer the codons making into protein. He knew that there would be errors, and there's actually error correction built into these molecules that we call proteins that reproduce sections of DNA. So there's and then there's copy errors on the spot. If there's an injury, we talked about the body knows that the skin is not supposed to be flopping around; it's supposed to be reconnected, and so it rebuilds that tissue. Incredible amount of foresight. And magic is not a causal factor. You can't say, it's just the way it is. Just the way it is doesn't solve the problem of how to get that way. Okay. All right. So we will ignore this slide and go on to the next one. Let's keep moving. So let's kind of wrap up the whole deal here. So where we've been, we've had 6 weeks on design, and as we think through where we've been, some of the things that we've done in the first lesson, just refreshing, we'll go a 2-minute recap of 6 weeks, right? So we talked about history, and we talked about the scientific revolution, some of the key players, and we talked about the timing of major ideas, the idea that geology was a forerunner to biology and many of the historic revolutions that happened in science. Session 2, we looked at design counterarguments. What are some of the things that people say that oppose the idea of design? And do they work? Can we explain what's happening that we see around us from what's inside the universe, or do we have to go outside? We looked at things like the mousetrap being an irreducibly complex system. If you take away any part, the rest of it doesn't work. And that's so many of our systems, with the sensors, the integrators, the effectors, all those things, have to have all the things in place or they don't work at all. We looked at origin of life in several different aspects. James Tour being a great guy. If you want to just be entertained as well as educated, James Tour, T-O-U-R, look for his YouTube videos. He's everywhere, and he's just a phenomenal thinker. Session 3, we did irreducible complexity. We looked at genetics and how that works. And then we also looked at the theory of biological design. We kind of introduced it. We're kind of back to it now. Some of the characteristics that concept has. Session 4 was our fun night on animals, and we looked at unusual animals like the platypus and the butterfly. And then in session 5 last week, we looked at a simple concept called gravity and examined how that works in terms of orbits, how orbits work, their conic sections, and how the planets work differently from each other. They're different geology, different densities, different orbits, different shapes, but always in a conic section. Something I didn't mention that I would do again, if I was going to do this again, I would definitely make sure to point this out, really important concept, the 400-to-1 ratio. So the moon is 1/400th of the size of the sun. The distance from the Earth to the sun is 1/400th to the moon and the rest to the sun. So that 1/400 ratio is what makes it so that we can have the moon superimpose over the sun in an eclipse, and we get to make discoveries about the sun's atmosphere. We get to see all of those, I'm forgetting all the terms right now, but all the stuff that comes out of the sun. We would not be able to see that. Now we can do I know that astronomers will make sort of a fake eclipse inside of instrumentation where they can get some of these readings, but you can't see the sun's atmosphere without a dark sky background. And so our sky gets in the way. But God made this relationship of 1/400, giving us an opportunity to discover. Much like we talked about, we're at a specific place in the galaxy where we're fairly far out, so we're not overwhelmed by all the sunlight from other stars, and so we don't have so much light pollution. We can see outside the galaxy. but we're not so far out that we're in danger of wandering space debris. So the outer reaches of the Milky Way galaxy sort of protect us from some of that. So God's put us in a perfect place to make observations. He's given us the intellect to make observations, and He's given us things like this that allow us to make discoveries and prove things that we wouldn't be able to observe otherwise. And so many of you saw the solar eclipse last year. These are a couple of pictures that I took that you would not see any of this without the eclipse being in the configuration where the planets, the moon, the earth, and the sun are. And then we had, actually, it was interesting, we had a little bit of cloud cover that made some things appear that we saw a flare here that we wouldn't have seen without the cloud cover, because it actually dimmed it just a little bit. So in the previous picture, we couldn't see it, but then when the cloud cover came by, it was just enough that we could actually see some of those flares. And then this session, of course, we looked at your designed body. We got to play with complex designs and complex systems. And finally, I want to thank you for for indulging me in sharing my dad's story along the way. And we got to do some interesting things with animation as well. So I've gotten to do some playing around with animation. That's been kind of fun. And he can do this all day long. But we'll put him to rest. So I guess my final question to you is, why does it matter? And the reason it matters is because God told us that He's the designer. And if we don't believe Him, we are discrediting Him. And God is not to be mocked. And so when God, when God says we shouldn't use His name in vain, if we are ridiculing God, all those people that say, well, this is evidence of a bad designer, so God doesn't exist. That's mocking the designer, because it turns out the platypus does exist. It does function, even though it's weird. But God designed it, I think, to make a point. He built it that way. He built hummingbirds and butterflies because He could, and because it demonstrates His creativity. And so when we question, when we assume that the part of the DNA that we don't yet understand is junk, we're really mocking the one who designed it and gave it a function. So I think it does matter. It also matters because if we take part of His word and we say, well, He says He designed it, but He really didn't, we're sort of discounting the other things that have to do with life and godliness and the things that have to do with our salvation. The fact that Christ died for us is in the same book that we're discounting because we're saying it was all an accident. And so it really does matter. Now, if I'm going to have a conversation with somebody who is an evolutionist or not open to these ideas, I'm not going to lead with this. I'm going to lead with, how are you doing with your relationship with God? Do you have a sense of consciousness that gives you a sense of guilt that we should talk about? Have you ever done things that you're ashamed of? There's a solution for that, and that solution is Jesus Christ. So I'm going to start there. I'm not going to start with these issues. And so that gets back to my philosophy that apologetics is really more helpful for us who are believers than it is for outsiders. Now, there are people who are non-Christians who are curious about these things, and some of them have been persuaded on the strength of the evidence from science as well as other places. Lee Strobel is one, Josh McDowell is another. There are a number of people that have come to faith because of the evidence that they saw in science and in Scripture. But for Christians, we should be open to this evidence, and it gives us confidence that the answers are all on our side. There are no new ideas coming out of evolution, as Steve Laufmann mentioned earlier. So we can be confident that we are on the side of truth, that the scientific evidence keeps falling in line behind God as the designer, and we don't have to be embarrassed by not being in the way of the world. So let me pray for us, and then we'll do questions. Anybody has questions, we'll entertain those, and I'll stay as long as you have questions or not. So, Lord, we thank you for these people. Thank you for the opportunity to think through these things and the way that you've designed the universe and the world. We are in awe of the complexity and the elegance of what you have done in so many attributes that we looked at. And so so we do thank you for being the God who is gracious to give us an opportunity to study these things and to see what you've done in your design. And so we worship you as we think about your word, but also the world that you've put us in. And we thank you for our time thinking through these things over the past weeks. In Jesus' name, amen. So, questions? Anybody have questions?
What happens after this?
We don't know. So Jason, as you know, did a phenomenal job with evidence for the flood. This is actually the end of 6 weeks, 4 different sessions of 6 weeks. So we've done 24 evidential series lessons this year. So we did the Greg Kokel tactics material, then we did evidence for the resurrection, evidence for the flood, and then evidence for God from design. And we're not sure about next year. So within the next couple of weeks, we will be sending you all a Google form. And please take a few minutes, and we'll try to not make it overly detailed and lengthy, but please give us some feedback. Tell us where we could have done better. Tell us what you found really helpful, and tell us what you'd like to see next. We're not sure if we're going to go to life groups or to another venue. Jason and I, we go where we're invited. We've been in the 4th and 5th grade classrooms for a couple of weeks, and it's been a lot of fun. We've done the flood, the Ice Age, and what was the other one? The Tower of Babel. Things that we don't usually talk about, the Tower of Babel and Ice Age. And Jason's a great researcher and has done a really good job putting that stuff together. It's been a lot of fun. So we go where we're invited. Great question, Jim. So you tell us where we should go next, and we will go. Okay? So that's kind of what's next. Other questions? Okay. Well, if you have other questions that come to mind, you have our emails. If you're not getting our emails, please make sure, I think we finally get the sign-up sheet over there, so please give us your email. If you have not been getting at least 2 emails a week, one before the class and one after, those will stop after one more. And if you don't want to get them, please let us know. That'll be on the survey as well. But do give us some feedback and make sure we have your contact information if you would like to stay on the list. Yeah, Don.
Okay, so you're not going to go through this with somebody who doesn't.
Correct. Well, I may go through a part of it depending on what's appropriate, but it's not going to be my major emphasis. Right.
So if you had 20 minutes with a person, how would you boil this down?
I wouldn't. Yeah, I would ask questions. I don't know who the great thinker was, but he said, if you had 20 minutes with somebody, how would you spend that time? He said, I'd spend 19 minutes asking questions and 1 minute answering a question or offering something. People like to talk about themselves. Gail and I have a kind of a joke running. Anytime I come home, and especially when I was in the airlines, and I'd be with a guy in the cockpit for hours on end, going to Europe or something, and I'd say, I was a great conversationalist this trip. That meant I asked all the questions, and they talked about themselves, and at the end they said, you're a great conversationalist. So people like to talk about themselves, and I want to draw them out. And so I want to know what makes them tick before I guess at what may be helpful. The classic example Greg Kokel uses that I remember is if somebody says, I'm a Buddhist, you don't immediately tell them what's wrong with Buddhism. You ask the question, what do you mean by that? When you say you're a Buddhist, what is it about Buddhism that really resonates with you? And so I ask a lot of questions. And then the next questions would be along the lines of, how did you come to the conclusion that you did about whatever? And then finally, if there's an opening in the conversation and they take a breath, you ask them, could I offer something to think about? And so yeah, this is, again, unless we're talking about something scientific, and there is an apologetics group that I've been a part of at UT Dallas, and there's one at UNT I've visited a couple times. There's a number of really good thinkers there that are not Christian, and they will ask really good questions. Sometimes they ask really dumb questions, but they'll ask good questions. Any questions are good when they get to conversation. So you go where they're interested, I think, and you try and address that. But apart from those rare people that do go to an apologetics thing that are not believers, most people on the other side would be completely turned off if you started talking about, species didn't come from other species and evolution didn't happen. That's not the place to start. So take yourself off the hook. You don't have to go there to get started. But if it comes up, maybe you'll have some nuggets that you can offer when you get to the point of finding out what they really believe. That's a long-winded answer to a short question. Anything else? Okay. Well, thank you again. We'll be here if you have questions, and you have our email. So thank you for your attention. It's been great having you tonight.